It's great to be back with another broadcast, or whatever you call it, a webinar. We've got this, but with this workshop on the counting principle. It is quite a interesting topic, and sometimes challenge to present this topic. And I think maybe you experienced that before. For a start, I would like to say everyone received the notes that I'm going to use as well. And these notes are from our new grade 12 Mind Action Series textbook. I think you can see it on the camera. Please take note, it says here, new edition. The new edition, we have a new edition for grade 10, 11, and 12. We still have our first edition as well for grade 10, 11, and 12, but now the new edition, 10, 11, and 12. And these notes are from the counting principle chapter in that textbook. What I would like to discuss with you today is to try to give you some ideas on how to present this. The problem with counting principle, and your learners will find it also complicated, in the sense that every problem is different. So they sort of understand this one, and then the next one they can't do again. So what I want to suggest to you is that you first discuss with them certain principles, that's what I call it, that they must keep in mind when they start a counting principle question. Now, I'm going to illustrate these principles by discussing examples, but these examples are fairly easy because it's about to see what these principles are all about. But we will get to the more exciting ones as well. So we're not only going to stick to easy ones. So you will see on this first page, you will notice there's a short little definition that I've put in here. And I said there that if task 1 can be performed on N1 ways and task 2 can be performed in N2 ways, then the number of ways in which both tasks can be performed is N1 times N2. So we need to, first of all, when we look at a question, we need to determine how many tasks are there, and then how many ways we can do every task. Now, if you now look at this first example on a menu, then I will illustrate to you what this definition is all about. Now, you will notice in this menu, I've got starter, I've got the main course, and I've got dessert. You can only select one of each. Now, the question is, how many different meal combinations are there? So what we need to do is, we first need to ask ourselves, how many tasks do we have? And you can see it's quite clear we've got 3 tasks. We need to select the starter, we need to select a main course, we need to select the dessert. So what I like to do, and I would recommend you to do it like this with your learners as well, I like to draw lines to represent my different tasks that I'm going to do. It's almost like you are building a picture on this problem, and that will really help you, in particular when they get more difficult. It's helpful. So now we do the first task. How many ways can we do the first task? And you will all agree that is 1, 2, 3 ways, so that is 3. And the main course, the second task, 1, 2, 3, 4, 5. So I put 5 on the second task, and then 1, 2, 3, 4 on the third one. Now the counting principles say, and what we read here at the top, that once you know how many ways you can do every task, so like N1 ways for task 1, N2 ways for task 2, then we just multiply N1 and N2. Now, to know how many meal combinations, we're just going to multiply these 3, and I think you're all happy with 60. So that is the number of meal combinations. You do notice it's a fairly easy question, but I believe that is where you need to start. You need to start with easy ones so that you take the learners slowly into the counting principle. So let's look at the next question. And the next question is also on the menu. You will see that is the B part of the question. I say a particular person wishes to have grilled king clip as his main course. How many different meal combinations can he choose now? So this person, there's still the 3 tasks, like we said, but now instead of the main course have 5 possibilities. Now we say the main course must be grilled king clip. So I believe you will agree with me that my main course now have only one possibility, namely grilled king clip. We call that a restriction. And we do that first. And now we add the rest. And this is still 3 for the starter and 4 for the desserts. And if we multiply, there will be 12 menus. So this is just to illustrate, first of all, how this definition works. What the counting principle really tells us. It says that once you know how many ways you can do every task, to know how many arrangements or combinations there are, you multiply those tasks. So then I would like to start with the second principle. So first of all is the definition. Now it's about repetition or not. And it's quite important that learners must understand if a question's got, if there is repetition allowed or repetition not allowed. Now you will see this heading, I say that on this one, that repetition is allowed. Now the question I took is a pretty straightforward one. I say how many 4-digit codes, you will see 4-digit codes, using digits 0 to 9 are possible if each digit may be used any number of times, so they can repeat. Now the important thing, first of all, is this 4-digit code tells us how many tasks we have. We have 4 tasks because we built these codes. And we're going to build these codes by using 0 to 9. Please make sure your learners know 0 to 9 equals 10 possible digits. I get it very often where they say to me, only 9 possible digits. They don't see 0 as a digit. So it's 10 possible digits. They may repeat. So if I do the first task, I think you will all agree I can do it 10 different ways. And because repetition is allowed, that means if the digit in the first position is 5, I can get 5 again. So that means this is also 10, this is also 10, and this is also 10. And that is what you normally get if repetition is allowed. And now when we multiply, we will get 10 to the 4, or for that matter, 10,000. So as you can see, that when repetition is allowed, then what we normally see is the number of ways we can do every task stays the same. So we get exponents, the 10, 10, 10, 10. And now you most probably see and already sort of anticipate what we're going to discuss next. And the next one, very much the same problem, 4 digits, 0 to 9. The only difference now is they may not be used more than once. So this is where repetition is not allowed. So let's do this one. So I'm going to draw my 4 lines to represent the code. And now I've got 10 possible digits. My first digit, there are 10 different ones that can be in the first position. But now repetition is not allowed. So whatever I placed in the first position, if it's a 5 or a 6, I can't use it again. So that means I've got only 9 left for the second position, then 8, and then 7. And we just multiply these, and the learners must give the answer. So it's pretty straightforward. So why I did these questions, and you notice I kept them the same, so that they can just see the difference between when repetition is allowed, and like repetition is allowed here, and when repetition is not allowed, like in this one. So in the next example, it's still on that there's no repetition. This one is where I took a word, and this word is action. And if you looked at previous exam papers, you will notice that it's a very common way of testing the counting principle in the matric finals. They quite like to give a word. Now, my word action, it's got 1, 2, 3, 4, 5, 6 letters. And these letters may not repeat. Now, normally, if they give a word in the exam, the examiners say you only rearrange those letters. So they don't always say there is no repetition, but a word means no repetition if they didn't say repetition is allowed. Now, we're going to do action now. As you can see, there are 6 letters. So I'm going to draw the 6 lines to represent the word action. 1, 2, 3, 4, 5, 6. And now repetition is not allowed. So when we do the first position, I think you're all comfortable. There are 6 possibilities for the first position. Any one of those 6 letters can be in the first position. But whatever is in the first position can't be in the second one. So then you will get 5, then 4, then 3, then 2, and 1. So you will notice that we also get it to decrease like it did here. The only difference is this one decreased to 1, where that one stopped at 7. And the reason why this happens is that we've got only 4 tasks, but we've got 10 available that we put in 4 different tasks. So it's 10 available, and then normally it does not go down to 1. But in this one, in the word action, there are 6 letters, and we've got 6 positions. So then it goes down to 1. And then counting principles say, once we know, we can just multiply these. And I think you are aware already that this we can write as 6 factorial. But the learners must give the answer and work it out. And I think if I'm not mistaken, it's 720 for that one. So the learners are welcome to use the factorial. The exam panel accept it, but they must work it out. And I recommend they use it as well, because it's so easy to make mistakes if you have like a 10 factorial and you try to multiply 10 times 9 times 8 times 7 on your calculator. A very good chance to make a mistake. When we use 6 factorial on the calculator, the chances of making mistake way more slim. So that is factorials. My suggestion will be that you don't discuss factorials in depth, because it is not quite a topic in our syllabus. It's only a tool that we use to do these calculations. At tertiary level, we go way more in depth into factorials, and then we also do operations on it. But for now, I think if your learners know what is the meaning of 6 factorial, or for this matter, 6 times 5 times 4 times 3 times 2 times 1, which gives you the 6 factorial. I gave 4 factorial, 3 factorial, 2 factorial, and 1 factorial. I didn't write down 0 factorial because I've got so many learners in the past ask me about 0 factorial. we don't use 0 factorial in counting principle, but it confused them because you maybe know that 0 factorial is also 1. Now, that is what they don't get. They look at 1 factorial is 1, and now they say 0 factorial is 1. How does it work? Now, I will not suggest that you waste time with it. The 0 factorial, which is 1, is there a very easy explanation, and I don't go into in-depth definitions because that sidetracked us from what we really need to do, and that is counting principle. But 0 factorial, you can't write as products. Like 2 factorial, you can write as 2 times 1. 3 factorial, 3 times 2 times 1. 0 factorial, you can't write as a product. Therefore, the answer is always 1. That's a principle that we have in mathematics. The same thing we get if you look at something like 2 to the exponent of 0 or 2 to the power of 0. That is also 1, because 2 to the 0 we can't write as a product. So that's just an easy, simple way that you can quickly explain 0 factorial. I personally, I don't even talk about 0 factorial. I just leave it. I think it's not so necessary for grade 12. All right, so let's go to the next one. So if I can just quickly recap with you, my first discussion, we did the menu, was to explain how counting principle work. Secondly, we look at repetition is allowed or repetition is not allowed. And now we look at restrictions. Now that very first question that we did, if I can just quickly turn back there, on the menu, you will remember the starters 3 possibilities, main course 5, dessert 4, and that is how we've got the 3, 5, 4 here. But when we did the B part, that was when we say a particular person wishes to have grilled king clip as his main course. So this main course of 5 is now restricted to 1, to only king clip. Now that is what we refer to as a restriction on a position. Now that is what we're now going to look at. So if you look at these, I say here at the top that we have arrangements with restrictions. And the first one we will discuss is a restriction on position. So we're going to look at similar questions than the menu, where we restrict positions. And if you look at this question, you notice that I took the word equations. It's quite a nice word to use in a discussion like this, because there are, I think, 9 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9. And all 9 are different. There are no letters that repeat. And you are aware we can get questions like this where letters repeat. I will touch on that later, because they are slightly more difficult than these ones, where all the letters are different. So we've got 9 different letters. We want to arrange it. No repetition. So the moment we arrange letters of a word, there's no repetition. And the first question I say, the first letter must be E. So if I draw the 9 lines, 1, 2, 3, 4, 6, 7, 8, 9, then the first position must be E. And I think you will agree there's only one way we can do it, because that is E. And they can't repeat, so we can't use it again. So now we've got 8 letters left. So now we start at position 2, and it's 8, 7, 6, 5, 4, 3, 2, and 1. And now we multiply. That's what counting principles say. Once we know how many ways we can do every task, we multiply, and the answer is then 8 factorial. If you don't mind, then we can leave the answers for our discussion in 8 factorial. Please tell your learners they will lose a mark in the exam if they don't give the final answer. The exam panel wants to get the answer. They don't only want to see 8 factorial. but I'm sure this is all okay so far. If we look at B, I say first letter is E and the last letter is S. So I'm going to draw my 9 lines again. And now first position is restricted. Last position is restricted to S. And first position will be 1. Last position will be 1. And now in between, there are no restrictions. And you agree there are now 7 letters left. So we go 7, 6, 5, 4, 3, 2, 1. And now we're going to multiply. And you agree in multiplication, this 1 in the beginning and at the end, it's got no impact. So the answer now, 7 factorial. If we restrict 2 positions. Now, I found it many times when I did this, then learners say to me, so that means that if we restrict a position, it's always the first and the last. I say, no, let's look at C. Here, we also have 2 positions that we restrict, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now it's not necessarily position 1 or position 9. I now say the second letter must be Q. And the 7th one must be O. 1, 2, 3, 4, 5, 6, 7, that must be O. And you agree this is 1 and that one will also be 1. Please make sure your learners are aware that restrictions they must do first. First restrictions before they do the rest. So now we've done the 2 restrictions. And now we say we've got 7 letters left. And we start from position 1. 7, 6, 5, 4, 3, 2, and 1. And when we multiply, we can see how many arrangements are there. And this one will also be 7 factorial. Because you will agree with me that this one and that one got no effect because of multiplication. So we're not finished with equations. There's a few more. Because another thing that I've got from learners is they start to think that when we restrict, it's always 1. And that is not the case. It depends how we restrict it. So you notice in D, I now ask for the first letter must be a vowel. So if I draw my 9 lines, they say the first letter must be a vowel. Now, you all know that we have 5 vowels in the alphabet. Now, we can't just put 5 straight away because we need to check how many vowels in this word equations. How many vowels are there? And the interesting thing is, and that is why this word is also so nice, is all 5 of the vowels are there. The E, U, A, I, and O. So all 5 vowels are in this word. So I hope you agree with me. The first position is then 5. Let's put the pen on. That will be 5. Any one of the 5 vowels can be in first position, but there's no repetition. So that means we've got 8 now left. So if we start in position 2, we've got 8, 7, 6, 5, 4, 3, 2, and 1. And when I multiply, this gives us 5 times 8 factorial. Just one thing to look out for that I've seen many times in the past is that many people want to put a factorial with 5 as well. But 5 can't be factorial because it's only one position. There's not 5, 4, 3, 2, 1. You will notice the 8 goes down to 1. So that is factorial. But the 5, only a number. 5 times 8 factorial. Now, as you can see on the last one, I'm back again on the vowels. So say 1, 2, 3, 4, 5, 6, 7, 8, 9. And I say first position is a vowel. So that is 5 of them. But now we place one, and then they also say the last position must also be a vowel. And I hope you're all happy that will be 4. Because all 5 can be in the first one, but then we place one and they can't repeat. So therefore the last position's got 4. So now we placed 2 of the vowels. So that means we've got 7 letters left. So we go from position 2, 7, 6, 5, 4, 3, 2, and 1. And as you now can see, that gives me 7 factorial. The 5 and the 4 are just positions. They're just numbers. So when I multiply this, then we will get 5 times 4 times 7 factorial. I will suggest that you tell your learners that they put it exactly like that on the calculator and just write down the final answer. 5 times 4 times 7 factorial. So I hope that is okay so far. So on the restrictions, so what we have is we have restriction on a position. And now we're going to start looking at the second kind of restriction. And that is what we call, and you will see it here, you call it groupings. Now, if we look at this one, and that is sometimes when some of these positions are grouped together. When we read this question, you will see how many ways can the letters of the word product be arranged if P, O, and C must be grouped together in any order. Now, before I draw the lines, what I always like to do as well, and I hope all of you can at least see my fingers. They're all here, yeah, looks like it. I like to explain this by using my fingers, and the children, they can physically see it if you hold up your hands and you explain it that way. You will notice the word product got 7 letters. 1, 2, 3, 4, 5, 6, 7. Yes. So we've got 7 letters. Of the 7, 3 is a group, P, O, and C. The rest is not a group. That's also something you must make sure. Your learners, when they say P, O, and C together, they tell me there are 2 groups. They also want to put the rest in a group. The rest is not a group, only P, O, and C. So I always say, this is my P, O, and C. This is the 3 that is a group. Then there's still another 4. So you will see the 4 and the 3, that gives me the 7 letters. Now this 4 is not a group. So I put it aside for a moment, and I only look at the 3 that is a group. And how many ways can I arrange this 3? And that is, if you think of lines, you will say 3, 2, 1. That means 3 factorial. So the group of 3, I can arrange in 3 factorial ways. Then you count it as 1, because it's a group, and this group is together. Now I bring the remaining letters, which is 4, and as you now can count, I now have 5 to arrange. So that is 5 factorial. So your answer for this question then will be 3 factorial for the group, and I multiply this with 5 factorial, and I want to make sure you understand why it's 5, because the group of 3, and there's 4, this 3, none of these 4 can move between them. And this group stays together. If this group moves, they move together, all 3 of them. So the 3 can be here, they can move there, they can move there, they can move there, or to the back. So the 3 can move anywhere, and that is why we count them as 1. They move as 1, if that makes sense. So that is how we do a grouping. And it's always important to determine how many groups. It's not always only 1. We can get more than 1 group, and it doesn't even bother how many in the group. If it's 2 or 3 or 4, it doesn't really matter. We do it the same. So we do the group first, and then we do the rest. It is for now an easy one like this one. So if I quickly make a drawing for you, that we just do it also with the lines, and you will see my 7 lines for the 7 letters of product. 1, 2, 3, 4, 5, 6, 7. And now I'm going to group the first 3. Well, it doesn't matter where the 3 are, but I'm going to group these 3. This is now the P, O, and C. And that will be 3, 2, 1. So this gives us the 3 factorial. Now, you see this box, you count it as 1. So it is 1, 2, 3, 4, 5 that you need to arrange. So we can now say it is 5, 4, 3, 2, and 1. So we multiply with 5 factorial. Because the group, please, the group you count as 1 together with those 4. And that's where you get the 5 from. All right, let's do the next one. There's more of them. And if there's still things you're not so sure of, I think we will address it here. In this particular question, I say there's a group of 8 people. There's 4 couples, 4 men, 4 women. And we seat them on a bench. How many possible seating arrangements are there if all the men have to sit together? You can hear the question is pretty clear. All the men. The question say nothing about the woman. But your learners will still say, if you ask them how many groups, they will say 2. Now, if you look at the second question, the B one, you see all the men must sit together and all the women. So I think you agree with me. The first one, in A, there's only 1 group. In the second one, we have 2 groups. So let's do this first one. Now it's 4 men and 4 women. So if I use my fingers, I've got 4 men, 4 women. The 4 women, I put them aside because they're not a group. The 4 men is a group. And to arrange the 4 men, that will be 4 factorial. Now you count it as 1 and you bring the 4 women, and then it's times 5 factorial. So the answer for this question then will be 4 factorial times 5 factorial. Now again, what we can do is we can draw our lines 4, 5, 6, 7, 8. And we say, let's say this represents the 4 men. Then we have 4, 3, 2, and 1, which is the 4 factorial. And now we have still the 4 women plus the group of men, which is then 5, 4, 3, 2, 1. And that gives you the 5 factorial. And they must just work it out. So let's look at B. Now we've got 2 groups here. So men is a group, woman is a group. So I put nothing aside. So the 4 men, I arrange them, 4 factorial, it becomes 1. The 4 women, I arrange them, 4 factorial, and it becomes 1. And do you now notice I still have 2 groups to arrange? So the 4 men is 4 factorial, the 4 women is 4 factorial, and now I need to arrange the 2 groups, because men can be first, then women, or we can switch them around. So I think you've got the answer for this one. It will be 4 factorial for the men times 4 factorial for the women times 2 factorial for the 2 groups, because we've got 2 groups to arrange. So 1, 2, 3, 4, 5, 6, 7, 8. So I can put here the men together, and there I put the women together. You can see the 2 groups. And this is 4, 3, 2, 1, 4, 3, 2, 1. So this one then gives you the 4 factorial. That one gives you that 4 factorial. And then I've got the 2 groups to arrange, and that is the 2 factorial. So I believe this is okay so far. Now, if we look at the next question, and I just draw a line over it here that we just can read it. I say each couple have to sit together, and there are 4 couples. So I hope you agree with me that we have 4 groups here that we want to arrange. So we've got the first couple, 2 people, the second couple, the third couple, and the fourth couple. So as you can see, I left openings in between to illustrate the 4 groups. If you want to box them, it's also fine. But this couple will be 2, 1. So that means 2 factorial times 2, 1, which is 2 factorial, times 2, 1, 2 factorial, times 2, 1, which is also 2 factorial. But as you now can see, I've got 4 groups. So I first arranged each couple, 2 factorial, 4 of them, and then I arrange the groups. And as you can see, it's quite clear. The groups are 4, 3, 2, and 1. So that is then the 4 factorial. They must put that on the calculator once off and just work out the answer from there. All right. So, ladies and gentlemen, the next one, an interesting one, and that is where I say to you, how many arrangements are there if men and women must alternate? Now, this is typical a problem where it's quite important that we draw the lines. So to see what is happening here, 4, 5, 6, 7, 8. So if I say it's a male, female, male, female, male, female, and male, female, they alternate. So now I start with the males. This male, any one of the 4. This male, any one of the remaining 3. This one, 2. This one, 1. You will take notice that in this question, they didn't say anything about repetition because it's people and people can't repeat. So we do the female, the males, and now the females, and that will be 4, 3, 2, and 1. Now, if you look, yes.
Sorry, there's a question here. How many possible arrangements if all men don't have to sit together?
Sure. They don't have mercy on me. That is quite a difficult question. What I will suggest, I'm not trying to avoid it, but I do have a question like that, not the same one, that comes later, where they refuse to sit together or they don't sit together. And then we must do something else. So if you don't mind that we leave it until we have it there, and hopefully I can answer your question then.
Okay. Thanks. Thank you, Jörg.
All right. So when you look at these 4 groups of couples, the 4 couples, then what basically this is about, if I have the 4 men and then I place the 4 women between them. So it's almost like this situation. And now what we're going to do is we can remove them. We can split them up. And can you see the group? So now we can say the men is 4 factorial times the woman is 4 factorial. But now there is something else that one must keep in mind. Now it's not about the 2 groups as such, because you can't switch the groups because they sort of like in between one another. But what one now must keep in mind is, you will notice that I started with a male. But the question didn't say you must start with a male. we can start with a female as well. So that means we can do this arrangement again, but starting with a female. So that means we can do the arrangement twice. And once we've done that, we must now say times 2, or you can say 2 factorial, or just 2 for the other arrangement. So it's similar to when we work with 2 groups as such, where you multiply with 2 factorial, because the 2 groups can swap around. This one is not groups that swap around, is that we start with a male, or we can start with a female. Just to mention something here, sometimes in these questions, they say to you 4 men and 3 women. Now, when you have 4 men and 3 women, and I just want to go back a little bit because I'm just looking for some space, because I just quickly write it for you. If I can just do it maybe here. And I say we've got 4 men, 3 women. And I want them to alternate. Now, if I alternate 4, 5, 6, 7, then it is 4, 3, 2, 1 for the males, and then 3, 2, 1 for the females. And do you notice this we can do only one way, because the males are more than the woman. If you want to start now with a woman, the last 2 positions will not alternate. They will both be males. So when the one is more than the other, you have only one possible arrangement. So the answer for this one will then be 4 factorial times 3 factorial. So we don't have a times 2 like we had in the question we just did, because that 2 was because we can do it again, starting with female. I hope that is clear to all of you. All right. So ladies and gentlemen, I'm now basically done discussing the counting principle, because these are the principles your learners must understand. And that is what they must look for. So when they read a question, they must first of all determine if there is repetition or not. Any physical things like people, books, clothes, no repetition. Letters and digits may repeat. So the question must say, tell us there what we need to do. So they must be able to say repetition or not. Then they must look for restrictions, either position or grouping. Now you will see I now start with probability. That is why we do counting principle, so that we use it in probability. And that is why probability is also part of the grade 11 probability. But I hope you agree with me, counting principle is not quite probability. It's a mathematical principle, but we use it to calculate probabilities. Now, I give the sort of the formula for probability again. You most probably still remember from grade 11, we've got the P of the event is the N of the event over the N of S. Now, this works pretty much the same. I just phrase it slightly different because this is now related to counting principle. So you will see I say the number of possibilities meeting the condition, or we can say restriction. So your numerator in a probability will be your restriction. Your denominator, total number of possibilities. That means no restriction. So below the line, no restriction. Above the line, there will be a restriction. So you can see when they test this, they also at the same time will test if the learners do understand this whole thing about restrictions and also repetition or not. So let's look at example 8. I say 5 men and 4 women are seated on a bench randomly. What is the probability that the 4 women will be seated together? Now, what I like to tell learners is that whenever you see they ask for probability, say the probability and do your denominator first, because the denominator has got no restrictions. There's 5 men, 4 women, so 9 people. So when we do the denominator, it's not about males and females, it's about how many people, because there's no restriction. So I hope you all agree with me. We can say in the denominator, it will be 9 factorial, because there's no restriction. Now we're going to do the numerator. And as you can see, this one say the women must be seated together. Now we've got 4 women and 5 men. And I hope you agree with me, this is only one group. Only the woman is a group, not the men. The question must say women together and men together. This one say women together. So women together is 4 factorial. You count it as 1 and you bring the males, and that is 5 of them, plus the one group, and that gives you 6. So this answer here then will be 4 factorial times 6 factorial. So if I can just explain it again, I say 4 factorial is the 4 females. It's the only group, and that is 4 factorial. Then you count it as 1, and then you bring the 5 men plus the group of women, which is 6 that I must arrange, and that gives me the 6. Yeah, I think I said it in Afrikaans now. The 6 factorial. Ladies and gentlemen, what I will suggest you tell your learners are that they must not work out the numerator and denominator separately and then divide the answers. They must put this whole thing as it is, that they use the fraction button on their calculators and they put above the line 4 factorial times 6 factorial, below the line 9 factorial, and they just calculate that answer. And they must give that answer in the exam. So I hope these probabilities, you will notice there's not something new. I just like and prefer that we do counting principle first. We discuss those principles, that they have a pretty good idea how to approach a question before we start with probability. Because now whenever there's a probability question on this, you will always have a restriction in your numerator and no restriction in your denominator. All right, let's just look at another one of this. Now, in this question, I say every person in South Africa every client of a South African bank has a personal identity number, which we normally just to refer to as a PIN number. That's now for your ATM card if you want to withdraw money or something. And they say it consists of 5 digits. Now, the moment I read this 5 digits, it now sounds to me like this is, if I can just draw the 5 lines, 1, 3, 4, 5, that I've got only 5 positions available because that is my PIN number, that represents my PIN. But now to take note, the digits I have available that I choose from is 0 to 9, so 10 digits. Now, like I said, explained to you before, the moment that I have 5 and I put 10 in it, if repetition is not allowed, and you will see in this one, I say repetition, digits may not repeat. Now, normally in a PIN number, in real life, they may repeat. In this question, I decided to say they may not repeat. Now, may not repeat, you will agree with me, these number of ways we can do it will decrease as we go on. But it will not give you factorial because it will not go down to 1. Because we've got 10 available in 5 positions. So I'm starting with position 1, and that is 10, 9, 8, 7, 6. So this is my arrangement. And you will agree this will be my sample space because I didn't apply any restriction here. I said a 5-digit PIN, 10 digits available, they can't repeat, and that is what I will get. Now, just to start the probability, this will be the denominator. Now, again, I will suggest that the learners just put it like this on the calculator, or leave it like this for the moment and keep it like that. I will show you just now. So now we need to look at what is the restriction. And if we read this, I say the PIN consists of 5 digits that we've got, chosen from digits 0 to 9. We use the 10 digits. Digits may not repeat. Yes. A PIN is generated. What is the probability? It will start with a 5 and end with a 6. So let's draw the lines. 1, 2, 3, 4, 5. The first one must be a 5. So I hope you all agree it's 1. There is only one 5. They can't repeat. I can't use it again. That must be 5, the first position. The last position must be 6. There's only one of them. So now we do the other 3 from the second position. And you will hopefully agree with me, we've got now only 8 digits left because we already now placed 5 as well as 6. And we now only left with 8. So we go now 8, 7, 6. You see my numerator? 8 times 7 times 6. Now, the moment you get this, quite easy to do, because 876 will cancel because it's multiplication, and your answer 1/90. And it works out quite easily that way. Otherwise, they can just calculate it on their calculators. So this is about probability. How do I use counting principle to do probabilities? So let's see what is next. Now, in this one, I say more advanced counting procedures. Now, the first one, the heading I give it is identical objects. So as you now can see, we're now going to move to slightly more difficult problems. But we still remember what we did and how we approached it. We will do the same here. What is different to this question, if you look at the word, you will notice the word is substitute. That is where letters repeat. You'll remember when I did the equation, the problem on equation with you, the word was equation, all the letters different. And I then mentioned to you, we will get to those where the letters repeat. Now, substitute, it's got letters that repeat. Now, what we need to understand is, if I look at these and I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters, if all of them were different, we would have said 10 factorial, because it's 10 letters, 10 positions, 10 factorial. But I hope you agree with me, 10 factorial is not the answer for this one. And the reason is, if I swap this S and that S, then the word is the same. If I swap this U and that U, the word will be the same. If I swap T and T, the word will be the same. So within this 10 factorial number of arrangements, some of those arrangements are the same, and we must remove them. And we do it by division. So we are going to divide. And the question is, what do we divide with? And we divide with those letters that is there more than once. So I look at my word and I say S. If it's there only once, then I move on. But S is there twice. So what you now need to do is you divide by 2 factorial to remove those identical words. Then if I continue, I say the next one is U, and there is another U. So that means we've got another 2 factorial we need to divide with. And then I look at B, and there's only one of them. Now for the B that is 1, one can write 1 factorial. You may do it mathematically correct, but it's not necessary because 1 factorial is just 1, and this is multiplication, so it's not going to have any impact here. So the letters that's there once, we just don't keep them, we don't look at them. So we use the S, the U, the B is there one, S we did already, now we add T. Do you notice we've got 1, 2, 3 of them? So that means we must times by 3 factorial. And I think we covered all of them now, because we've got the T, there's an I, but there's only one of them. U we used already, and E, there's only one of them. So this will be the number of arrangements for the letters of the word substitute. 10 factorial over 2 factorial times 2 factorial times 3 factorial. Now, ladies and gentlemen, the next question, still on substitute, it's only the B part, but now I ask for probability. Now, this probability question, one must be very careful. But please, if you just focus with me, then you will see something. I want to show you what exactly happens here. So if I want the probability, then I always like to write down my denominator first. And my denominator, I hope you agree with me, is this, because there was no restriction. It was just the word substitute. How many ways can we arrange those letters? 10 factorial over 2 factorial, 2 factorial, and 3 factorial. So that is what we're going to write down below the line. So we say 10 factorial over 2 factorial times 2 factorial times 3 factorial. But now we must do the restriction because that is the numerator. And this one say, if the letters of the word are arranged randomly, calculate the probability that the word will start and end with an S. Start with an S, end with an S. And you will notice in the word, we've got 1, 2 S's there. So what will we do? So if I just quickly want to draw this line, the lines for substitute, then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now they say the first one must be a S, and the second one must, or the last one must also be an S. Now, what many people like to do or ask if you can do it, they say this S, there's only one of them, and this S, only one. It is correct. One can do it that way. I do it slightly different, and I just want you to hear me out and to see why I do it. And I treat these 2 S's as different. So my approach very much, as we started this question, that 10 factorial, I treated all the letters as different. And then I divide with the ones that repeat. Now, I want to do the same thing here. I'm going to treat these 2 S's as different. So we can call it S1 and S2, for instance. So that means this position, there are 2 possibilities because any one of the 2 can be in the first position and the other one in the last position. So I treat them as different because we still need to divide in any case. So let's do the rest. So now I placed the 2 S's, and now I want to know what about the rest. So you will agree we've got now 8 left. So it's 8, 7, 6, 5, 4, 3, 2, and 1. And when we multiply, you will notice that that will give us 8 factorial, and there is a times 2. So that means what we need to do is we need to say that this is 2 times 8 factorial. And now I must also divide with the letters that repeat. Now, the S repeat, which is 2 factorial, then it was, what was the other one? The U that repeat, and that is 2 factorial, and then T that was 3 factorial. Now, if you look at this, and I've got this fraction over a fraction, and you agree with me, we normally tip in times, then this denominator and that denominator will cancel. So it means we will be left with 2 times 8 factorial over 10 factorial. And we just work that out. And that is why I kept those S's as different. Because if you didn't do it, if you wanted this to be 1 and that to be 1, then I hope you agree with me, we will not divide with that 2 that represents the 2 S's, because we already treated them as the same. So you don't divide by it. I'm just worried that confuse your learners. And I want to stick to the same thing and say, we always divide with the letters that repeat. So you treat them as different originally, and then you divide. And then when you do have that approach, you will get it that these denominators will always cancel. Otherwise, this one would have been 2 factorial times 3 factorial over this one. Still possible to work it out. It will still work, because you can see this 2 and this 2 factorial basically will cancel and gives you that. Because the moment I treat them as the same, I will not have that 2. I will only have 8 factorial, and this 2 factorial will not be there. I like to treat them as the same, as different, and then I just divide at the end. And I hope that makes sense. So whatever you feel finally how to do it, I think this is what I found to work the best for the learners. All right, so ladies and gentlemen, we have a few problems left. This is now where we get to the question that came in earlier, that people don't want to sit together. That is what we're going to discuss here. If you don't mind, if we can quickly take a break, say 5 minutes or so, if you want to get something to drink and maybe just take a walk, and I will see you in 5 minutes. And then we continue with the rest.
Thank you, Jurg. Okay, yeah, you can just quickly take a break. For those that have joined us late, we are recording the webinar, and we will share the link with you afterwards. So you will not miss out if you've joined late. Okay, we'll see you in a bit. Jurg, are you ready to continue?
I am ready.
Okay, just before you continue, it was mentioned that specific question was in the supplementary exam in 2024, and that is why they are asking this question.
Yeah, I unfortunately don't have the question. I haven't seen the supplementary paper, but I hope this example 11 will explain that principle that they tested there.
Okay.
But I unfortunately don't have that question. But let's see. So, ladies and gentlemen, you will see what I've got here. I call it counting the rest, and I refer to it as the not rule. Counting the rest, and it's just the name I gave for it as the not rule. We have this rule in probability in grade 11 as well. We also talk about the not rule. And there, the not rule comes from your complementary events, where we say the P of not A is 1 minus the P of A. So now, in this particular case, you will notice that I didn't use P, I use N, because P is probability. We only use the number, so therefore N. So that is why I say the N of not A is the N of S. Here we use N of S and not 1. You will agree in probability, 1 is your sample space. And it's the N of S minus the N of A. Or the N of A is equal to the N of S minus the N of not A. So the sentence I wrote there above, I said there that it's sometimes very difficult to count what is described exactly, and much easier to count the opposite. And then we subtract it from the sample space. But let's have a look at this problem, and then you will exactly see what I mean by this. I say 6 learners are to be seated on 6 chairs in an auditorium. So 6 learners are seated on 6 chairs. So here's 6 learners, 6 chairs. The chairs are your tasks. 6 learners. They can't repeat, it's people. So therefore, we will get factorials here. You will notice I say, how many ways can these 6 learners be seated? So there's absolute no restriction here, nothing funny. So all we have is we draw our 6 lines, 2, 3, 4, 5, 6. And now we're going to seat these 6 learners. So it goes 6, 5, 4, 3, 2, 1, which will then give you the 6 factorial. So this one, straightforward. The moment they will ask us now probability, this 6 factorial will be the denominator. Let's look at the B part. How many ways can they be seated if 2 particular learners refuse to sit together? Now, what I would like to do before we continue with this one, I would just like to explain to you again the opposite of this. So we have 6 learners and 2 insist to sit together. So we have 6 people in total, 2 want to sit together. So you agree we have a group of 2 and we've still got another 4. But it's only those 2 that is a group. So that is 2 factorial. You count it as 1, and then you bring the 4. So it's then 2 factorial times 5 factorial. So you agree with me, the moment they tell us that they are a group, it's quite easy to work out. In this case, if 2 people want to be seated together, we know exactly how to do it. But how do we calculate it if they refuse to sit together? And I almost want to say to you, I've got no idea if there's, in any case, a way to do it. I will not even try it. So I will rather use the not rule. So what I'm going to do in this one is I'm going to work out the sample space. Well, I don't need to. We've done it already, 6 factorial. And from the 6 factorial, we're going to subtract. And I'm going to just take you back to this one. Maybe this one will be applicable. The n of not seated together is equal to the n of s, that's the 6 factorial, minus the n of a seated together. Now, if you think about it, if you know how many ways they are seated together and you subtract it from the total, then you agree what is left is they are not seated together. So how do we write it down? We're going to do exactly this. So we can say the n of not seated together is equal to my sample space, 6 factorial, subtract, seated together. So now I want to show you again. I want to do the grouping again. So 2 is in a group. So they are seated together, the 2, which is 2 factorial. And then I bring the, how many? It was 6, yeah, 2 and 4. 2 is a group 2 factorial. And then I bring the other 4. So that is 5 factorial. So I subtract 2 factorial times 5 factorial. And that is basically the only way I can suggest to you how to calculate these arrangements where they can't sit together. You must work with the opposite. Now, I don't have that question. I will try to get hold of it, to look at it, but I'm pretty sure it's maybe similar to this. I have another one of these that I would like us to do. And this one, many people find quite confusing. I say using digits 1 to 9. Ladies and gentlemen, please take note, 1 to 9. There's only 9 digits. It's not 0 to 9. You see, they very often do this in exams. They sneak it and the learners just see it and they remember at school, you said 10 and they just use 10. Make sure they know 1 to 9 is 9. And we have a 5-digit number. So we say using digits 1 to 9, how many 5-digit number can be constructed containing at least 1 6? Digits may repeat. So we've got 9 digits available. We want to build 5-digit numbers, but these 5 digits must contain at least 1 6. Now, the meaning of this 1 6, 5-digit numbers, 3, 4, 5, the whole thing about this at least 1 6, you will agree with me, what we are looking for is, we are looking for 1 6, or 2 of them, or 3 of them, or 4 of them, or 5 of them. So there can be 1, 2, 3, 4, or 5, because it's at least 1. They only give us the minimum, but it can be more. Now, it's quite a task to try to work it out. So what we can think about here is that if we want at least 1 6, what is it we don't want? We don't want no 6s. So that is what we're going to calculate. We're going to do the opposite. So we don't know how to calculate at least 1 6. So what about we calculate no 6? So then it means I've got 5, 1, 2, 3, 4, 5 for my different digits. These digits may repeat, yes. And when I use all of them, then it's 9, so I will get 9, 9, 9, 9, 9, which will give you 9 to the 5. So I hope you agree with me, this will be my sample space. Now I want to calculate no 6. So it means we've got only 8 digits, and they can repeat 8, 8, 8, 8, and 8. And that gives us 8 to the 5. So now, how many ways can we do this question? Very easy, 9 to the 5 minus 8 to the 5. Because this is your sample space, and this is the opposite. So if I can go back to this little formula, the not is what we are looking for, that at least 1 6. So then we say sample space minus no 6. So I remove the 6. I know how many ways I can do it without the 6. I subtract it from the sample space, and then we are left with at least 1 6. So I hope that this makes sense to you. One must think about it carefully, but it's always in this, some of these questions, it's easier to work with the opposite. If you don't mind, I also added a few questions from old matric papers, some of them pretty old, but quite nice ones. I added, I think, 3 of them, nice questions. This first one is covers almost everything except probability. I still think they suppose at least to ask probability in one of them. But this is a one on a concert tour to Durban, East London, PE, Cape Town, Bloemfontein, Johannesburg, Polokwane. And we want to arrange their tour. First question is, there are no restrictions. How many ways can we arrange this tour? Now, these are 7 cities, and these cities can't repeat. So there's no repetition. There's 7 of them. And your learners will now start to pick it up and to say to you, no restriction, can't repeat 7 factorial. And they're quite right. 1, 2, 3, 4, 5, 6, 7. So you will get the 7 cities, 7, 6, 5, 4, 3, 2, and 1, which will give us that 7 factorial for the first one. In number 2, they say the first performance must be in Cape Town and the last performance must be in Polokwane. So it's 1, 2, 3, 4, 5, 6, 7. First one is Cape Town. There's only one Cape Town. So I restrict first position to 1. Last position, Polokwane. So you agree these 2 cities are fixed on this program. That is only 1 and 1 in those positions. In between these 5, no restriction. So we place 2 cities. We've got 5 cities left, and that is 5, 4, 3, 2, and 1. And you will agree this is 5 factorial. Like I said before, this one and that one has got no impact. When we do the third one, they say the performances in the 4 coastal cities must be grouped together. The 4 coastal cities. Remember, there are 7 cities here. So when I look at my 4 coastal cities and my 3 non-coastal, it's only one group. They didn't say coastal together and inland together. They said coastal together, one group, 4 factorial. Count as 1. Bring the other 3 cities, 4 factorial. So the answer for this last one, 4 factorial times 4 factorial. Please take note, there's only one group, only the coastal cities is in a group. That is 4 factorial, which you count then as 1. And then there's still another 3. You bring that to the 3 plus the group, and that gives you 4 factorial. And they just calculate that. You will see this is a pure counting principle question. This little question where the word is maths. the first time I looked at this question, I thought, wow, looks quite boring, until I start to read that second one. But let's do the first part. We've got 5 letters available. They're different. They can't repeat. And they say how many different 5-letter arrangements can be made using all the above letters. And I think you will now be able already to tell me mentally the answer. We've got 5 letters, 5 positions. They can't repeat. 5, 4, 3, 2, 1, and that gives us 5 factorial. When we do the second one, please take note, it's a probability question. Now, the moment I see probability, I would like my denominator. And you agree that is number 1 when we multiply those. So the denominator, 5 factorial. We now need to find the numerator. That is what we want now. Now, what is the restriction? If I can put it in my own words, is a group. Now, if we just think about it, just stop there, don't read the rest. If I change the question slightly and I say to you, S and T must always be together, then you will agree with me there's one group of 2 and there's still another 3 letters. So then we will say 2 factorial becomes 1 times 4 factorial. But let's read what they say. They say S and T, but they must always be the first 2 letters of the arrangement. So what is interesting about this question is that I just draw 5 lines, 3, 4, 5. They say to us that S and T, so it's 2 and 1, so it's 2 factorial for that little group. All right. I don't know where this is now. It doesn't show. Let's just see what is going on. Don't know why it doesn't want to show my lines now. I'm not sure. I want to draw 5 lines and I do it on my side, but I see it looks like you can't see it. So what I want to do is I want to draw 5 lines like I did here in the previous one, in this one. And then I want to box the first 2 as S and T. And then I'm going to do the rest. I just can't figure out why suddenly I can't see it. Nou, kom.
Het het delay.
Ja.
Massive delay.
Okay, let's just see. There's one line. Ladies and gentlemen, I just quickly want to see, it looks like there's a delay on my internet, and that is why it doesn't show when I draw the lines. I just quickly want to wait and see if I can get it to work better. So let's say 1, 2, 3, 4, 5. Okay, they come slowly. But in any case, the first 2 positions. So what this question is about, this S and T is a group also fixed in positions 1 and 2. So this is the only question where you get that I could find in old papers where positions and grouping is together in the same question. And that is why I think it's worthwhile we talk about something like it. So they say S and T not only together, but S and T in the first 2 positions. So now on the first 2, I will have 2 and 1. and that is then 2 factorial. Now the question is, what do we do with the rest? The rest is not a group, but the rest can't move in position 1 and 2. So if you think with me about it, I've got this 2 S&T, and I've got another 3. All right? Now, this 2 S&T is 2 factorial. But now this 2 factorial, this group of 2, are also fixed in position 1 and 2. So when we sit with these 3, this group are not going to move between them. So it means this 3, we can't add the group like we did before. So 3b then times 3 factorial, and not 4 factorial like we did it before. Because we will have 3, 2, and 1 for the last 3 positions. We will have those. Okay. All right. It sounds like it's okay on your side. You can at least see. Sometimes it just comes a little bit later. There you can see the 3 to 1. So I hope you understand why this one works different than a normal grouping, because it's not only a grouping, it's also positions. So that 2 S&T stays in, they can switch around, but they stay in position 1 and 2. The other 3, they stay in those positions because they can't move here and S&T can't move there. So I hope it makes sense. And we don't treat them as 2 groups because there's only 1 group. So that will be your numerator. So we will say 2 factorial times 3 factorial above the 5 factorial. And now we can just simplify that as 2 times 3 factorial. And then the 5 factorial, you can write as 5 times 4 times 3 factorial. 3 factorials will cancel, and you get 2 over 20 or 1 over 10. I hope that makes sense. So, tiny little question, looks innocent, but there's a little trick that one needs to understand. So, let's look at the last question that I've got for you here. This last one I quite like, to be honest with you, because this question covers most of what counting principle is all about. It's about 7 different shirts and 4 different pairs of trousers you want to hang in a cupboard. The clothes have to be hung on the rail. How many different ways can the clothes be arranged? You see the wording of the first question. It's not about shirts, it's not about trousers, it's about clothing items. So 6.1, very clear, there are 11 clothing items, 5, 6, 7, 8, 10, 11, and you go 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, which will give you 11 factorial. And when you work this out on a calculator, you will notice it is a very big number. So 11 factorial, no restriction. It's 11 clothing items. They're different. There's no repetition. And we place them on a rail. When I go to number 2, they say to us, in how many different ways can the clothes be arranged if all the shirts are to be hung next to each other and all the pairs of trousers are to be hung next to each other on the rail? So I hope you will agree. My question when I read this, and I have grade 12s in front of me, I will read it and I will ask, do you agree it's grouping? How many groups? And this one I have 2 groups. You see, it's very clear. Shirts together, trousers together. Now shirts, there's 7. Now just pretend this hand represents 7. And there are 4 pairs of trousers. So we've got 7 shirts, which is 7 factorial, times The 4 trousers, 4 factorial. So 7 factorial times 4 factorial. But I hope you agree with me, that is not the final answer. I have 2 groups now. So I have now the shirts first, the trousers second, but we can switch them around. So that means times 2 factorial for the 2 groups. So shirts in a group, trousers in a group, both of them. In the third one, they say, what is the probability? Now, when I see probability, I always suggest to the learners, write down your denominator. And then you focus on the numerator. We want the probability that a pair of trousers will hang at the beginning of the rail and a shirt will hang at the end of the rail. So I just want to draw these lines again. 2, 3, 4, 5, 8, 9, 10, 11. They say this first position must be a trouser. Now, when you ask the learners how many ways, many of them will say 1. Then you ask them, is there only 1 trouser? No. How many trousers? 4. So any 4 of the trousers can be in position 1. Then we go to the last position, which must be a shirt. There are 7 different shirts. It's not 1 if I restrict it to a shirt. It can be any one of 7 possible shirts. Now we placed 2 clothing items. So we're left with 9. So I go 9, 8, 7, 6, 5, 4, 3, 2, and 1. So what your numerator will be is 4 times 7 times 9 factorial. Please take note, like I said it before, the 4 and the 7 are not factorials. It's only a number on one of these positions. The only time you get factorials is if they go down to 1. Then we get factorial. This one, not too difficult to calculate, or they can just use the calculator. We say 28 times 9 factorial over 11 times 10 times 9 factorial. They will cancel, and I get 28 over 110, and we can still simplify it further. They may use a calculator, give the answer in a decimal or as a fraction. It doesn't really matter. So, ladies and gentlemen, this was my last question. So I don't know if you have any questions. We still have a little bit of time. If you would like to ask a question, I will try to explain as far as possible. But otherwise, if there are no questions, then I hope this will help you. If this helps you, I'm sure you will be able to help the learners. And that is the whole idea.
Okay, no questions at this time, Jurg, but someone just, Leslie said, thank you so much for this. I'm actually teaching this tomorrow. Good timing.
Oh, great stuff. So Leslie, use your notes that you've got, and it will guide you through your lesson, and then you just add more questions finally. I'm really pleased. Thank you very much.
Thank you so much, Jurg. We really appreciate the time that you took out of your busy schedule also to be here today and to talk to us and teach us some more on the counting principle. And yeah, a lot of thank yous coming through. And we're all really, really happy for this time that you took. And yeah, all the best. Looking forward to the next webinar.
Definitely. Hopefully we see one another soon. Have all of the best with your grade 12s, in particular with this topic. Maybe a last comment, ladies and gentlemen. Counting principle is around about 7-8 marks in the please look at your time when you teach this topic, that you don't spend 3 weeks on it, because then it's going to be a problem. So a little bit lesser time, but it takes time for the learners to grasp this. So you can't do it in 3 days. So, but all of the best for you, as well as for your learners for this term. Thank you very much, and have a good afternoon.
Thank you so much, Jörg. Just to recap again, we are recording, or we have recorded this session, and we will share it with you as soon as possible after the webinar. So be on the lookout for that in your emails, and we will also post it on our website, and we'll send you the link. So that's all from us. Thank you, everyone. Have a good evening.
Goodbye.